Hi, and welcome to 5.1 Friction Intro and Static Friction. In this lesson, students will be able to describe what factors affect the frictional force, and students will be able to calculate the static friction between two surfaces. You see, there's two different types. There's static friction and then kinetic friction. For now, we'll just deal with static. So what exactly is friction? Friction is the force exerted by a surface as an object moves across it or makes an effort to move across it. So it doesn't necessarily have to be moving. There could still be a frictional force there, as we'll talk about when we talk about static friction. What exactly is static friction? So when talking about just friction in general, there are two things to consider. Number one, do all surfaces exert the same frictional force? Or do different surfaces exert different frictional forces? And how can we quantify the difference in a calculation? How are we gonna plug this into an equation? The second factor that we want to consider is what other factor can increase the frictional force? Is it just the surfaces, or is there something else that we can change that would increase or decrease the frictional force besides just the surfaces? So to answer the first question, yes, the type of surface does matter. And we measure a surface's roughness using something called the coefficient of friction. Mu, the Greek letter mu, is the symbol for the coefficient of friction. Mu does not have units. Mu is a scalar quantity, meaning there's no direction associated with it. It's just a magnitude. It's just measuring the roughness between two surfaces. So there would be no direction with that. And the magnitude represents the larger the magnitude of the coefficient of friction, the rougher the surface is. So if it's a very low coefficient, then there's not going to be that much friction between the two surfaces. So you might be saying, oh, and then when mu is equal to 0, the surface is frictionless, but that is just a hypothetical thing. But as you've seen in the problems that we've been doing, a lot of times they say neglect friction. So technically in those hypothetical problems where there's 0 friction, the coefficient is 0. Anyway, you might be wondering yourself, what the heck is that letter? It's just a Greek letter, and it's called mu. And here's how you write it. This might bring you back to your grade school stuff, right? So the way you write, you start below the line, and then got a little messed up here. Hold on. Okay, you start below the line, and you come up, and then you just make a normal U. Okay, so it looks like an M, and when I write it really fast, it'll be like that. I'll just scribble it, and it'll look like an M. But technically, you want to start below the line. You could even come straight up and then make a U like that. So start below. If you want to be fancy, that's when you get like that, something like that. Okay, it's not an M, it's a mu. It's a Greek letter mu. So practice writing it like that. Just a line and then a U. So where can we find the coefficients of friction? It's kind of like a weird abstract concept for now, so it'll help to see because we're talking about the two surfaces and a number associated with it. So where is it? Look for it in your reference table. It's actually right on the front page over here in this table here, the approximate coefficients of friction. And they'll tell you two different surfaces for each one. So rubber on concrete when it's dry, when it's wet, rubber on asphalt when it's dry and when it's wet. So you might ask yourself, what type of problems would have rubber and concrete or rubber and asphalt? Think about it. Yeah, tires are made of rubber and roads are made of concrete or asphalt, and they could be dry or wet. If it's raining, it'll get wet. So those are the coefficients that you would use if you're talking about a car on a road. And you can see there's a column for the kinetic friction, which I mentioned before. We're not going to do that today. We're going to start with just the static friction. So when you're pulling out your numbers, you might see, okay, it's a tire on dry concrete. You're going to look at this line here and don't just automatically pick the first number you see. You have to look at the situation and think to yourself, okay, is this thing moving or is it stationary? So the whole thing with static is that it's stationary. So just don't forget that there's a second column here. What else we got? We got rubber on ice, so that might be, what do you think? A hockey puck, maybe? Wax ski on snow. And then these are the typical ones: wood on wood, steel on steel, copper on steel, Teflon on Teflon. They like coat non-stick pans with Teflon. And as you can see, it's a very low coefficient of friction compared to everything else. So the lower the coefficient, the less friction there's going to be. So that is your coefficient of friction. And this is basically all hidden information in the problem. The word problem will say this, and you'll have to come here and say, okay, I could plug one of these numbers into my calculation now. So it's good to know where this is. So yeah, there's friction between every single surface you can imagine, because a frictionless surface, perfectly frictionless, is impossible. Even for typical metal surfaces, this is under like a very high-powered microscope. Yeah, it's not completely smooth. Wood surfaces, obviously they're rough. And then even if it's polished metal, there's still a rough surface when you get back down to it, or even porcelain. So there's going to be friction here. So that answers the first question. Do all surfaces exert the same frictional force? No, we use the mu, we use the coefficient of friction to differentiate between surfaces. Then the second question is, what other factor can increase the frictional force? What do you think? So, you know, don't think about the surface material or, anything like that. What's something else we could change to increase or decrease the frictional force? So right now, think about it. If it's the same material for each block and the surface here, which will have a larger frictional force? In other words, which will be harder to move, the 5 kilogram block or the 10 kilogram block? Which one? It's going to be the 10 kilogram block is harder to move. But why? What if it's like this? Pretty much the same, right? What if you exert, so it's not just the weight is the point of this. Yeah, 10 kilograms would be harder to move. But what if you're like pressing down on it so that there's a component of your applied force pushing down? We saw that before, right? What changes when you push the object down or you squeeze the surfaces together? What causes that to change? Yeah, we have the weight and we have this. It's the normal force. The normal force will increase when you do that, and the normal force increases if the mass increases. So the thing that squeezes the surfaces together, we can measure using the normal force. So the higher the normal force, the more friction there will be between the surfaces. And it doesn't matter what the materials are made of. We're not changing that. We're just changing how much they're being squeezed together. And if they're squeezed together more, it's going to be harder to move because there's more friction. So changing the normal force acting on the object will increase or decrease the force of the friction if you decrease that normal force. How are these factors related to the frictional force? Is it an inverse relationship, direct relationship? What do you think? Well, we said that for the coefficient of friction, the larger this number is, the larger the frictional force is. So what kind of relationship that is that? As one gets bigger, the other gets bigger. That's a direct relationship. And what about for the normal force? If we increase the normal force, if we squeeze the surfaces together more, we're increasing the normal force, then that's going to make it harder to move. So the frictional force also increases, and that's another direct relationship. So both of these factors have a direct relationship with respect to the frictional force. So what do you think the equation might look like? So far we have mu, we have Fn, and then we're calculating what's called F lowercase f, all right, for the force of friction. So what would the equation look like? Looks like this. It's the fun equation. And even though this isn't a U, we still say in the physics biz, this is fun, because sometimes you could even write it like, F for friction is equal to mu N for the normal force. Oh, it's so much fun. Okay. So this is the the friction formula. The coefficient of friction times the normal force gives you the frictional force. And as you could see, they're both directly related. to the frictional force. If I double the coefficient, then this doubles as well. Cool. So where is that formula? Where's that formula on your reference table? The coefficient of friction is on the front, but where's the equation? It's on the back. Here it is right here. There's the friction formula. And then I always like to point out, okay, so we're dealing with a Greek letter. The Greek letter mu is located down here. All the Greek letters are kind of at the bottom. Remember, this is all alphabetically listed for you. So we have the coefficient of friction right there. And then where's the normal force? Wow, look at all these different forces we have here. Okay, so not only do we have the normal force, we have the frictional force listed as well, and the coefficient of friction, just in case you forget any of that stuff. So I promised we talk about static friction. So it's a force that resists the initiation of sliding motion between surfaces that are in contact and at rest. So they have to be at rest and you're trying to start sliding it across. So at this point, I always ask my students, okay, you have a desk in front of you. Very gently try to start pushing your desk. It is possible to exert a force on the desk, a very light force. You're exerting a force there, but the desk isn't moving yet. All right, so there must be a force balancing out how you're pushing on your desk. Are you pushing on your desk right now? Very lightly? Don't move it yet. Don't move the desk. We're not talking about kinetic friction. We're thinking about the static friction that's holding the desk in place. Even though you're applying a force, there's an equal static friction force opposing you. Now, I know you're really strong, so you can exert a stronger applied force than the maximum static friction that exists between the desk and the floor. There's a maximum static friction that can exert. It's not like an infinitely large amount of static friction that resists every force that could possibly be. No, you're stronger than that frictional force. You could overcome that maximum static friction and then start moving the desk. So the question in the word problem is going to be, how much force does it take to start moving it? In other words, what is the maximum static friction that you need to overcome between those two surfaces? Okay, so the static friction, or FFS for static, acts opposite the applied force. If we were going to have our free body diagram, your applied force that you were pushing on your desk with, and then the static force, it's equal and opposite in this case. It's because it's balancing out your applied force. We're not moving the desk yet. It's at rest still. And remember, friction always acts parallel to the surface of contact. So these two surfaces, in our case, the desk and the floor, those two surfaces, the frictional force acts parallel to that interface there. Now, as you increase your applied force, the frictional force actually increases with that because it stays balanced out until the maximum static friction is reached. And if you increase your applied force just slightly more than the maximum, then you're going to start moving. And then when you start moving, there's still friction there, but it's not static friction anymore. It's kinetic friction. So static means stationary. And you could remember static means stationary. That's how I would like to remember it. You could make the word stationary out of it. So if it's stationary, if it's not moving, it's static friction. Okay. And then as soon as it starts sliding, it's kinetic friction, just like we did our kinematic equations. Things were moving around. Kinetic friction is when you're sliding, you're moving across the surface. So we got two examples, and then we're done. So let's see what we got. You could try these on your own if you want, and then you could pause the video, read the question, and then see if you did it right. It says a 5-kilogram wooden block is at rest on a wooden table, and that's all they tell you. Okay, so let's see what we got. We have the mass is equal to 5 kilograms. We know we can assume we're on Earth. G is equal to -9.8 meters per second squared. What else? It's at rest. Okay, so VI is equal to 0 meters per second, I guess. We're actually not going to use that piece of information, but what else do we know? What else do we know? Oh, it's a wood block on a wooden table. Remember, that's going to give us some hidden information. If you look at the front of your reference table, what is the coefficient of friction between wood on wood? Go ahead and look. Go ahead and look it up yourself, and then so pause the video here. I had to pause it myself because I wanted to make sure I wrote it down. I should have put in an animation that shows it, right? So this is going to be your first time making the mu, the coefficient of friction, is equal to, what number did you pick? There's two there. Did you pick 0.30? Or did you pick the coefficient that says 0.42? Well, this one is the mu k, and this is mu s, and we're at rest. So we definitely got to use that static friction in this case, okay? So we're going to use that one. Now the question says how much force is required to start the block moving. Technically, they're asking for the applied force. All right, how much force is required to start the block moving? The strategy is to really find FFS. Okay, and technically we're finding the maximum. You don't have to write max every time because really that's what we're looking for. But yeah, that's what we're looking for, the maximum static friction. So we're going to use this. And oh, we don't have the normal force. What are we going to do? I'll tell you what we're going to do. We're going to make a free body diagram and remind ourselves that when it's just at rest like this, okay, we have the normal force here. And then we're going to make an applied force, and then there's FFS, right? Nice. Okay, so the net force in the y direction is equal to Fn plus Fg. In the y direction, you're not accelerating up or down, so the net force is equal to 0. The normal force is what we want, and Fg is equal to mg. You could do it like this. Sometimes I'll just write Fg equals mg on the side, but I'm kind of proving that Fn is equal to this. So Fn is plus the mass times g is, there's the negative 9.8 meters per second squared. So your normal force is equal to positive, because you add it to both sides, positive 49 newtons. And again, if you wanted to just, instead of writing a net force equation like this, you could just on the side go like this. And then by looking at your free body diagram, you can just say, okay, yeah, sweet, the normal force is equal to positive 49 newtons, okay? Either way is fine. In any case, now we have enough information to find the frictional force because we're going to use the static coefficient and the normal force that we just found. So you write the fun equation, F is equal to mu Fn. And remember, we're dealing with static. So I like to write the S because as you look at the reference table, don't forget there's the static column and the kinetic column. So sometimes people automatically pick one number without thinking about it. It's static because the block is at rest. It's stationary. It's not sliding across the table yet. That's kinetic friction. We're going to do that tomorrow. The normal force we found to be 49 newtons. So 49 times 0.42 gives you 20.58 newtons. Remember, this is the maximum static friction that can occur between a wooden block and a wooden table when that wooden block is 5 kilograms and it's not being squeezed together. The normal force is just equal to that weight. So that is the maximum static friction that can exist between those two things. If you go any larger than that, then you're going to start sliding. So that's good enough for our answer too. If you just left this, even though we said in the beginning, it says how much force is required to start the block moving, technically they're looking for an applied force of 20.58 newtons. And if you wanted to be really specific, you could go like this, an applied force that is greater than that. But really, you know, they're looking for the number that's the maximum static friction. If you exert just a hair more than that, you'll start moving. So that's good. Now, part B, think about it. It says, what would the frictional force be if the applied force is 10 newtons? Pause the video and think about it. Well, if the applied force was only equal to 10 newtons, then does that mean our frictional force, we found a number, it said 20.58. Is that what happens there? If that's true, then the frictional force is greater than the applied force. So the forces are not balanced and you start accelerating backwards. This person would go this way because the frictional force is greater. No, actually, remember, this is just the maximum static friction that can occur there. And we said in the previous slide that as you increase your applied force, the static friction also increases. But if it's only 10, you're not at that maximum static friction yet. So what's the frictional force going to be? That's also going to be 10 newtons. And you're not going to be able to move that block until you get to the maximum static friction and then overcome it. So yeah, the forces are balanced out right now. And you're not moving that block yet. It's still stationary, still static friction. Cool. So number 2, I like to do this one too because, yeah, it's a little bit different. It says you're trying to push a 20 kilogram crate across a horizontal floor. The material of the crate and the floor are unknown, but you determine that it takes 100 newtons to start the crate moving. In other words, the maximum static friction is 100 newtons. What is the coefficient of static friction between the crate and the floor? So I like to ask this one because in this case, they're looking for mu. And a lot of times people go right to the reference table and they look for something that says crate and floor. And that's very general. It's not on the reference table. Sometimes you'll have to calculate mu, but it's okay because we have an equation where we could do that. So let's start by making a free body diagram. So we have Fg and Fn, the weight and the normal force. And they're saying if you exert an applied force of 100 newtons, then that's going to be your maximum static friction as well. That's the force that it takes to overcome it. So we want to do F equals mu Fn, but we need some more information first. So let's write our givens. And the unknown, again, is the coefficient of friction. So again, it's kind of a two-step equation. And this time I'm going to do it the lazy way. I'm just going to do Fg equals mg. Plug in the numbers. And you get a weight, a force due to gravity of 196 newtons going down. And sometimes in the free body diagram, I won't make it negative because the negative is really just showing the direction and the arrow takes, does that job. So the normal force then, just by looking at our free body diagram, we've done enough of these, we can say, okay, that's equal to 196 newtons, even though it would be better to make your net force equation, which would look like that. Not totally necessary every single time. Now that we know the normal force, we're ready to do the friction formula. So FF equals mu Fn. What if I told you this friction formula really came from finding the coefficient of friction? So if you divide both sides by Fn, sorry, that's FF, there we go, divide by Fn. Okay, these cancel out, and you get the coefficient of friction. By definition, is a ratio of the frictional force that exists between two objects. You could experimentally find that, divided by the normal force, Fn. And this, by the way, is the reason why the coefficient of friction is unitless, because the force of friction is measured in newtons, and so is the normal force. It's also measured in newtons, and a newton divided by a newton cancels out, leaving the coefficient without units. So let's start with this version of the formula and then plug in our numbers. And remember, we're dealing with the static friction here. So the coefficient of static friction is equal to the frictional force, 100 newtons, divided by your normal force, which is 196 newtons. When you do that division, you get a coefficient of static friction of 0.51. And that's it. There's no units for this, again, because the newtons cancel out. So that's a pretty typical coefficient of friction between two surfaces. It's less than 1, so that's pretty reasonable. Okay. Yeah, so that's static friction and coefficient of friction and this Greek letter mu. Okay, a lot of new stuff for this one, but we're going to continue tomorrow with kinetic friction. So what happens when you start moving across the floor? All right, you start accelerating or even at a constant velocity across the floor, then it's kinetic. So yeah, that's about it. Thanks for watching and have a great day.